My name is Pramod. I work as Director of Engineering in Data Fabric Solution in MSL. MSL stands for Memory Solutions Lab, and it's in Samsung Semiconductors down here in San Jose. It's pretty nearby, actually. So I'm going to talk about how we have actually used CXL along with our performance value add component, which we call it as Cognos. Cognos is the memory platform software, and it has many components. And one of that component, which is more performance oriented, we call it as Cognos auto tier module. So CXL along with the auto tier module, how it has actually shown us improvements both in terms of performance and the TCO. And this is something which we have tried with something very real to something near to a real application. So what I'm going to cover today, I'll give you a quick background, how we started working on this and what is the origin, motivation about all this exercise. And a quick recap on, of course, this session is going to be about memory expansion. So a quick touchdown on like what is the current challenges, why people are going for CXL, right? Why not use the things? Of course, then the CXL will touch base on the CXL memory hierarchy, very usual term. I think all the session prior to this has talked about this. So I'm not going to talk too much on that. A quick recap on CXL protocols and all, quick. And then we jump to the Cognos, which is the memory software platform, about the memory orchestration, and then the performance enhancing value add feature, which is basically the auto tier module, which I just mentioned. And then we will focus more on something what we have really run and using the benchmarking, standard benchmarking like YCSP. And of course, followed by the conclusion and the potential future work. So it started, the whole effort actually started with one of our interaction with our customer, and the customer was basically using a in-memory database in their real production system, and they had a pain point in terms of memory because their application was actually memory bound, and every time they want to scale up the memory, they have to add the nodes. So that is something which they defined as a problem statement for us, and then we worked with our product management team to kind of emulate what is their production system in our internal labs. We did not have any direct access to their production system, so we took some certain inputs and we kind of emulated that workload using the standard benchmarking tool like YCSP. So we used YCSP, but the goals and everything of the benchmarking was coming based on the production system, which one of our customers was using. So that's where it started, and since memory expansion was the main definition of the pain point, so we started looking at what all things we have in our internally. So we have, Samsung has a good portfolio on CXL products. So we start exploring that what is the CXL product we can use for this particular experiment. And we decided to go with something what we call as CXL.mem. I'll come to that, but that's, I have more slides covering that. That's the whole basis of the experiment which we have done. Now, taking a step back, so what are the current challenges what we have? I think many of us already know that, but I just thought like just to keep the story, going in line. So why can't somebody just add more DDRs, right? So you cannot add, there is a limitation on memory channel. Like you cannot just add it because, of course, there is hardware real estate which goes out. You cannot just add it like that. Of course, when it is combined with physical characteristics, like you have more pins, you have to deal with the signal integrity and noise, and of course, the people who are actually working on the real, say, writing the RTL code and all, they have to go through the routing complexity, right? And of course, it all results in higher manufacturing cost. Right now, so given that you cannot add the DDR channels, so what the people do now? So they just add more nodes. So adding more nodes for a memory-bound application, it's not a it's not an efficient scale-out option, right? And of course, there is a memory stranding issue where you have an application where you have server nodes where you have attached memory, and this memory is actually calculated based on your, say, peak load or very near to the peak load. But most of the times you don't run in the peak load, so you don't use all the memory which is being attached. So that's when we introduce a CXL, right? So you see, so this diagram is repeated in different forms in the previous sessions also, but I'll just touch base that, yeah, you have on the top side of the memory pyramid, you have all the faster, smaller capacity memory tiers, and the bottom is normally the storage. And what we are doing here is that we are trying to have the CXL-based memory, and there are two kinds of memories which we have explored for this particular experiment. One is called CMMD, CXL Memory Module DRAM, and CXL Memory Module Hybrid. So these are actually Samsung devices which you have. So CMMD is already in the market, and the CMM Edge is something which is probably in the POC stage. But in our experiment, we have used CMM Edge because it's the hybrid one. It has a DRAM inside, and it is backed by the NAND flash also. So it gives you higher capacity. So that's the device which we have used. I'll come to that in a bit. Quick recap on CXL, open standard. It is supported by 3 core protocols, the IO, .cache, and .mem. So IO is basically for the link initialization, management, discovery of device enumeration, interrupt handling, DMA, all those things, standards thing. And this is kind of the main inevitable protocol for any of the CXL device. The other 2 protocols makes the device type, right? I mean, based on, is this a device which supports a .cache? .cache is where you are actually trying to access the processor memory to get the cache coherency. And .mem is, at a very high level, you can think of like the load store operations going on top of CXL, right? So, so all the memory devices, say CXL memory devices, you have to support .mem. The memory device type of our interest is the type 3, which is basically any kind of memory expansion devices we are going to use. Okay, I know that this slide is repeated many times. Okay. Yeah, so this is actually taken from the CXL standard page, so this diagram might be repeated many times. All right, so now jumping to what is it which we have done? So we have taken a distributed in-memory database. It can be anything like, say, Redis, Gemfire's SAP HANA, or Memcache, right? So it's all distributed, and we have deployed it in a cluster. So in our experiment, we have used 3-node cluster, but our hypothesis-based baseline cluster is kind of a 150 node, hypothetical based on certain inputs from our customers, one of many customers, and we have taken that as our, the baseline, and then we have scaled it down for our experiments, and we have scaled all the parameters based on that. So if 150 nodes, say, processes 750 million transactions, so how does it look like once you have 3 nodes, right? So that's our basis of the whole experiment. So this is a very generic view, so I am going to drill down more as we move forward. So in a general distributed in-memory database application, so I take one of the node where this is actually running. And I'm trying to expand this. You can see that, okay, there would be many instances of this in-memory database server in a physical node, right? So you can have multiple server instances running in a physical node, and all are sharing the same system memory. And you expand the system memory, you will see that, okay, there are different kind of, it's the same, coming from the same tier pyramid, which I just showed earlier. So you have DRAM, the one on the top are faster, the one on the bottom are slower one, but higher capacity. So I just, we just arranged it based on that. And then what is it which the Cognos memory orchestration or the tiering component inside that is bringing in? Is basically, we have the auto tier module, which is trying to scan through all the hot pages from the lower tier and move it up, and all the colder pages move it down. So this is something which we have developed, and we have done some kind of optimization based on the workload which we have run. So we have found that based on the workload, you can actually optimize the way your algorithm is working. So generic view, let's go to the experiment which we did, right? So as I mentioned that we kind of took the actual application, what is the workload they are doing, scaled it down to 3 nodes. And we set the goals for us for, in terms of TCO, that we should be able to reduce at least 30% of the TCO. And the more important point is the SLA parameters which we could derive from the real application, right? So we could see that with 150 node, our baseline application, each node should be actually giving a throughput of around 30K ops per second, right? So, and we are targeting for 30% reduction. So it means that once your number of nodes are reduced by 1/3, each node should be able to have at least 3 times the throughput. So that's why you see that. So it is 30 multiplied by 3. So it should be 90. So we took our target as 10K ops per second, right? And the latency which these applications were tolerant to is that if our I/O is able to complete within 1 millisecond, the application can survive with that latency. So that's how we kind of derived that. If it is longer, maybe towards the end? Or? Yeah, sure. Sure. Yeah. No, so yeah, so these two would be enumerated. It's just the NUMA node for the application. So when you're running the application, then you bind to these 2 nodes, and then you give it this particular information to our auto tier. Yeah, it sees both. Yeah. Okay. Sure. All right. So going a little bit further into our experiment. So this is the setup which we used. So we had 2 set of experiments. One is we ran it on single node and the 3 node, as I mentioned. So we used the Intel SRF machine. It's a dual socket machine, total 128 core. And each node had 512 gig of DRAM. And the one you see it as Cognos, please read it as Cognos has the CXL memory, right? So it's basically CXL memory plus Cognos as in software. And here you can see that it has 2 terabyte of CXL memory. So it has 2 CXL devices, 2 CMMH devices, 1 terabyte each. So that's how it is 2 terabyte. And we used 200 gig network. Of course, the network was not a problem. We never seen the network getting saturated. The YCSB configuration, see, again, these configurations are all coming from the application which I just talked. So we used a 400 key and 700 value key value thing, and the read-write ratio, again coming from a real application, it was 2:1. For single node, no redundancy. For multi-node, redundancy of 1, meaning 2 copies if you have multi-nodes. And the data size which we used for the baseline without CXL, we used 160 gig. And with the addition of 2 terabyte extra, we could run almost 5 times more of the data size. So you can see how the data size has impacted here. Okay, so drilling down a little bit more on the setup which we used for single node. We used one client for running the YCSB client, and this is where all the the queries are injected from here. Goes over the network to 200 gig network, and this is single node. So you have 2 sockets, and we used 2 Gemfire instances, not Gemfire. It can be any in-memory database. Each server instance is binded to each CPU, so we used 2 server instances, and the server instance which is running on each socket is seeing the DRAM and the CXL memory as NUMA nodes, and we did the memory binding between the DRAM and the CMM edge. So this is what we did for single node. The 3 node is kind of scaled out version of the same thing. So you have the same thing replicated into 3 different servers. The only thing is, like, we had added 2 client servers, again connected over the network, and the network was never saturated. So even the 200 gig was like over provisioned in that way. Okay, drilling a little bit deeper again to give more details about exact configuration which we used. Same thing, we used whatever I have showed it was a dual core machine, 128 cores. The main thing which I would like to highlight here is how you will see the NUMA nodes here. So total 512 gig of DRAM and split into 2 nodes, each 256 for each CPU socket, and 2 CXL devices, right, 1 TB each. This is what the application sees, and since we had 2 application instances, they kind of were binded for, say, one of the application binded to 0 and 2, and another one was 1 and 3. Quick overview on the workload size. So, as I mentioned in the previous slide, it's the 400, 700, the key value pair, and the data size which we tried was 160 gig and 800 gig. If somebody has used YCSB, you can see that there are some parameters which where we set the record count. So it is 80 million record count per client, per YCSB client, and the operation per YCSB client was set to 200K, and we had total of 10 such instances of YCSB client. So the total operations is 2 million over the whole cluster. Okay, so that's the setup which we have. Now maybe we can just go to the test results. So this sets up the setup what we have actually ran. Going to the test results, so I'll have the summary first, and then maybe we can actually go into more details about individual, the test runs we have run, the trends what we have seen and all. So the key takeaway here is definitely you can see. I'll take single node first and then go to the multi-node, the 3-node cluster. You can see clearly that the data size which we were able to run is 5 times more than the baseline which does not have the CXL, right? So the direct benefit, which is directly reflecting to the TCO, yeah, it's the 5x improvement which we have got. And whenever we go to CXL, one of the concern is, of course, how does the performance look like? And we set the target for 100K per node, and the latency target to be, around 1 millisecond. And what we have seen is that, yeah, the throughput actually went down when we went from DRAM to the CXL, but it was still under the accepted limit. Again, just want to reiterate that these limits are all coming from a real application. So it means that if we go with this solution and have a real deployment, it should most likely meet the real application SLAs. In terms of latency as well, we were able to observe that, okay, of course the latency went high when we started using CXL, but again, still it was under 1 millisecond, both for the read and write. Going to 3 node, again the same capacity advantage we have got it obviously because we are using 2 terabyte extra memory coming from CXL. But how was it about the SLAs, the throughput side? Again, the same thing, we got the throughput lower, but still we could maintain it higher than what we set for ourselves, right, the targeted SLA. We saw that on the latency side, the write latency was slightly higher, but when we checked with our customer, the customer's response was that, yeah, it is very much within the tolerance. So it's okay to be, having 5 to 10% going up and down. So yeah, so this is kind of the summary. Now I'm going to go more deeper into what were the trends when we run many other different applications, right? So let's start with the baseline which we ran for DRAM. So this is, again, the single node setup using only the DRAM. You can see here, some of the variables which we used was the concurrency, like you have a client which is having a number of, how many, parallel operations this any of the in-memory database server can handle. So we had concurrency as one of the factors. The other thing was the number of operations per client which can be injected into these servers, right? So you can see that the first 3 cluster, this is run with the concurrency of 10 cross 5. So 10 cross 5 means that in the YCSP you have 10 clients and each client is having 5 threads each. So you can consider the concurrency to be at 50. So there are 50 parallel threads accessing this the in-memory database server. And other 3 set of bars is basically when we have raised our concurrency from 50 to 100. And within each concurrency, we are varying the operations per client. Here you can see, I don't know how much visible is that. So this is like 200K ops per client, this is 500K, and this is 1 million K, right? And you can see that the trend here is that when you actually increase the concurrency, the throughput is kind of increasing on that basis. The throughput goes up. Within the same concurrency limit, when you increase the operation count, the latency per IO is actually decreasing because you have more IOs which can be processed. So the latency per IO is kind of going, it's going down. The same trend here also. So for the 200K, the 200 concurrency with 200, the latency per IO is going down. Now let's see that once in the single node, once the DRAM plus CXL comes in, how the things are going on. So I'm not going to focus on the memory capacity increase, that's already given. We would more focus on how the trend looks like in terms of performance. So again, this first 3 cluster graphs are for 10 cross 10 cross 5, and the next one is for 10 cross 10, where you have. So these 3 are for concurrency at 50. These 3 are for concurrency at 100. Again, the same trend is actually followed, right? You can see that the throughput actually increases when you are actually increasing the concurrency. And within the same concurrency, you can see the latency is kind of sliding down a little, but not the same level of latency improvement you see per IO with DRAM, but it's kind of slightly coming down. One of the factors which we were interested is that now we are actually doing tiering here because you have the CXL, so there is the tiering going on. So auto tier module is active. How much is the overall CPU impact to this, right? So you can see this particular graph is the one which is showing the CPU impact. What we have seen is that the CPU is always, around 50%. We have never seen going more than 50. This is kind of the 49, but not much of the CPU impact. All right, so moving forward. Yeah, sure.
So with regards to the statement of Gen 1 CXL,
oh yeah.
Is that you're talking about CXL 1.0?
No, so yeah, that's a good catch here. So this is CMM-H Gen 1. Like we had 2 generations of CMM-H within Samsung. So this is a POC device. So right now what we are using is 2nd generation of CMM-H. So it's like an internal term. It's nothing to do with the standard.
Okay,
so.
but it's still Gen 5 PCIe, or what was
So this was Gen 4.
This was Gen 4, and then
The new one is Gen 5, yeah.
so the 2.5x reduction in bandwidth that was experienced, or degradation, that was a bandwidth degradation
Yeah.
from the DDR5 server connected solution.
Yeah.
And still, you basically achieve the latency you're looking for.
Yeah. Yeah.
And the latency that is measured here in the millisecond or below, how is that measured from what was the latency of what?
So this is the latency from the YCSB client. Sorry? Oh, okay, sure. So the question is that the latency, how is the latency measured here? So the latency is actually coming from the YCSB client point of view. So the whole, you have the I/O going to the server over the network, and the server do the processing and then respond back. So the time is calculated here. So it includes even the network traffic also. Yeah. All right. So moving to 3 node. So in this slide, we are just going to focus more on the throughput and the latencies. Again, it's the same thing. Just the single node you have you have the things replicated over the other 2 nodes. Here we actually, since we have more YCSB clients, we can have more concurrency now. So you can see the first 2 clusters are where we have the concurrency at 20 cross 5. So this is 100 concurrency. So then you have 20 cross 10, and then 20 cross 15, and then 20 cross 20, which is 400. So here in this experiment, we have tried more of concurrency, right? And again, this is the baseline, which is having only the DRAM. And this, you can see the same pattern here. When you have more concurrency, the throughput actually increases accordingly. But once we moved from 300 concurrency to 400, it kind of saturated there, right? So it became kind of flat over here. On the latency sides, it's kind of a similar pattern which we saw in the single node. Within the concurrency, the latency per IO is kind of dropping. But as you go higher with the higher concurrency, the latency kind of go up when the concurrency goes high. Now, how did it impact with the CXL? Same experiment which we ran, and you can see that we were seeing the similar pattern when with the increase in concurrency. So every increase in concurrency bumped it up, and towards the concurrency of 300 and 400, the throughput kind of flattened there. So we kind of preserved a similar characteristics when we moved to CXL. All right. One thing which I would like to mention here is that in the 3-node, you have the redundancy on, which means that every operation on each server is replicated to the remote also over the network, and it's a strong consistency model. So you replicate it on the other server, and till this guy is responded, the operation is not completed. So that's the model. So this includes the replication time also. All right. Yes. Yeah.
So when you say update latency, do you mean, so update means the client has said, hey, write or retire some new data or update some data, existing data.
Right.
It's not just a read to it, right? So normally, once the client said, okay, go write this, is it waiting for a notification to come back saying your data has been retired, and that's what you mean by the update latency?
Yeah, so the question is that what do we mean by update latency, and what is the time which is measured for this update? Yeah, so the update here is that basically the update instruction is triggered from the YCSB. So YCSB says that, okay, go and update this key with this value. It goes to the server, and server actually internally might read and modify and then do the write. And then since these are standard in database servers, we did not go deep into that, how exactly they are doing, but this would be the case. But for the replication, yes, once it actually updates here, it also updates on its replica server also, and it waits till it grew the ACK and then come back, and this is where the latency is measured.
So there is a notification back to the client saying, yes, your data has been updated?
Yeah. Because it's waiting for the update. It's not like there is a notification, but it's like, so YCSB give a update instruction, and then it is waiting till the server comes back and say that, yeah, your update is done. Yeah. Yeah. Yes, yes, exactly.
And when you say concurrency, are you saying in YCSB you control at what time simultaneously you issue so many reads? That's what you meant by concurrency?
Okay, so the question is that what is concurrency mean here? So the concurrency is a YCSB parameter where you can actually say that how many instances of YCSB clients you can spawn, and you also have an option to say that each client, how many threads it can have. So if you have 10 YCSB instances and 5 threads each, so you have concurrency of 50, like effectively 50 threads are accessing the server. Right, so moving forward, so we did some kind of extrapolation because as I mentioned earlier, the actual system is pretty large, right? So we just did it for 3 nodes. So how does the trend looks like when we kind of scale it out? How does that look? So we did a kind of extrapolation, like we had the numbers with a single node, 2 node system, and the 3 node. And we could see that how the throughput actually keeps on scaling when we added more and more nodes. Again, just want to reiterate that apart from the single node, all other configuration has the redundancy on, so the replication also comes in picture. So we see that, okay, the it's kind of scaling up. We could not try like more number of nodes, like 10 nodes or 20 nodes, because of we did not have that many nodes to try it out. But this is just an extrapolation exercise. And how does the vertical scaling, like scaling up, look like? So what we found out that as we add more and more memory, of course, the throughput comes down, but we could see that it is still able to maintain more than 100 k ops per second, at least till the point which we have tried. We have tried, I think this is the total 5 TB we have tried. In fact, as we speak, we are trying, say, 10 TB setup also. And we have seen that, okay, it is still able to maintain 100 k ops per second as the throughput. All right, so coming to the conclusion, so we have seen that the TCO was one of our motivation factor when we started the whole exercise. So when we saw that, of course, adding the CXL directly gives you bump up in the memory per node. It makes your node more memory dense. But along with the auto tier module which we have developed, we could increase its performance such that it still meets the expected performance, right? So that's something which we tried to do. So yeah, so it was all around the reduction in TCO and maintaining the SLA. Yeah.
Clarification on the TCO assumption. You're saying the number of nodes required for a particular workload.
Yeah.
So you're assuming that the assumption is, that's what I'm looking for, the assumptions of how we're comparing A versus B in terms of TCO enhancements.
I did not get the last portion, so.
So based on what assumptions of comparison was the TCO enhancement calculated? So basically you're saying you reduce the number of nodes to achieve a certain workload, but is it based on, there are many ways to calculate TCO. One of them is to add memory to an existing node, replace the 16 gigabyte DIMMs with 128 gigabyte DIMMs. Was there any similar, or just looked at physical node replication of an existing size?
Yeah, so our assumption was that these, okay, so sorry to repeat. Yeah, so let me repeat the question. So the question is that what was the assumption for our TCO calculation? So we assumed that the servers which we have used is going to be there is no heterogeneity in the servers. First thing, that is something which we have assumed. And we have seen that, okay, what is the application pain point here? Is it a memory bound or compute bound? So we have seen that it was never a compute bound application which we have used. So we could always actually scale up the memory without getting constrained at the compute. So it was a scale up assumption that, okay, we actually make the node more denser and denser, so that for the same kind of workload you need lesser nodes. And of course the exact TCO calculation would base on what is the exact server you are going to use, like what is your CPU, maybe you can go with a single socket or dual socket, and what is the server you are using, even the server, the space also, like is it a 1U server, 4U server, all these things matter when in the TCO. So that's why deliberately we haven't done the exact server based calculation, but since we are getting a 5x capacity improvement, assumption is that at least the number of nodes should be able to reduce by at least by 1/3, because we the SLAs which we have calculated is based on that. So per node right now is say 30K ops per second, which is the current per node throughput. And when you add, say, when you reduce the node by 1/3, of course, each node has to deliver 3 times better, right? So 30 becomes 90, and that's how the 100 has come. So that was our calculation. So that even the performance is derived from that node reduction.
Yeah, it's an assumption, but yeah, I got it.
Yeah, okay.
And it was confusing because you were showing 3 servers and all that. Where did you show the reduction in server? Where did you show, okay, I have DRAM only.
Yeah.
Now I require 3 servers. Now with CXL memory, I'm down to 1 server. I don't think we showed that.
Yeah. So as I mentioned earlier, oh, sorry. So the question is that why there is no evidence of reduction in server in the presentation, right? So when I started, I mentioned that we have a baseline cluster, which is a 150 node, and we scaled it down to 3 node, right? So if 150 node goes to 50 node, what would be the performance expectation from each node? Yeah, so 3 times. So that's how, so when it is 150 node, each node should deliver 30K ops. So once it is reduced to half, it should be 100. And that's how the 100 has come. Yeah. Yeah. All right, going to the future work, we are working on doing some data prefetching. I think there was a talk by the previous session about using, the AI for predicting and all. I think similar effort we are also pursuing, where we are trying to see how the prefetching can be used. Samsung do have devices which support device prefetching also. Say, for example, the CMM-H, which has the DRAM and the NAND flash. There is a tiering within the device. So it supports the device prefetching also. So once we have the device prefetching and the system level prefetching going together, I think the tiering effectiveness will definitely be improving. And as in the previous session, there was device pooling and sharing. So yeah, based on the load, you can actually use more memory or not use more memory, pooling use case. Or if there are use cases where you're sharing the memory, you can use the CXL sharing to, reduce the overall per unit memory usage. The memory orchestration, it's all the auto tiering, which I have talked about. And the final thing is we are working on supporting multiple tiers. Like right now, our experiment just showed DRAM and CMM-H, but we are also working on, more than 2 tiers. That's the effort which we are pursuing right now. Thank you. Questions if thank you. Yeah.
First slide you showed, you said CXL fabric.
Oh, okay. So let me go to. So the question, this? Yeah. So the question is why we are showing the CXL over fabric. So this is something, this is a generic view, and the slide is just showing that if you have a distributed in-memory database kind of application, you can actually use any of these options. So that's what it is saying. It can be direct attached or it can be over the fabric. But what we have used is this. So, yeah, it's all direct attached, yeah.
And also you related to that, right? This is not distributed, right? You said you have replicated the database on all the 3 servers.
Yeah.
So where is the distributed database here?
So the database which we have used is running on multiple nodes, right? It's all controlled by a single locator, which is kind of the orchestrator sitting on the top. So the client which I have shown in this.
Have redundant copies of the database 3 times?
Yeah. So that's all managed by the database itself. It's not something which we are, database supports that.
I took distributed database and okay, you have 100 terabyte database, now you put not 100, whatever, some number, and you split it into 3 and host it on 3 different hosts. That's another way to look at a distributed database. But that's not what you did.
Yeah, that's not what we did, yeah.
You just increase the number of servers to improve the throughput.
Yeah, so our focus was more about focusing on the capacity story and meeting the SLAs. Yeah. Sure.
Because I know about the CMM Edge and I talked to the Samsung people. By the way, my name is Anil Gogole. I'm the marketing chair of the CXL consortium, and also I work for Intel. My talk is coming up next. But thanks for showing the use of CXL in this conference. I'm going to do the same. But coming back to my technical question, based on what I know about CMM Edge, you are essentially, let's say you use 1 terabyte of NAND, and you have some DRAM buffer, let's say 64 gigabytes or whatever, I don't know what you guys are using. You are advertising the whole 1 terabyte as the memory space of that CXL memory, right? So you better have and the DRAM is just a cache. So if there is a miss in that thing, now what is your latency? Because the flash is going to be at least a few tens of microseconds, right? So at that time, the CPU has to keep on waiting.
Yeah.
So what's your worst case latency? I mean, worst case 1 millisecond? I mean, some other papers have said, no, it can be 5 or 10 milliseconds. I mean, they are using very fast flash.
Okay.
And so I was surprised how you can get 1 millisecond.
Okay. Yeah. So the question is that since we have used CMM Edge, which has a flash behind the scene, and there is a device cache, yes, that's correct. So there are chances that if the I/O hits the NAND flash, what is the overall latency, right? So I don't have the tail latency number for the device as of now. The number which you have seen is something which YCSB has experienced, and this is something like a day-long test, right? It runs over the day, and then it just sees that, okay, whatever P99 comes in for the whole day, it is like, within that 100 millisecond. But of course, if you say,
1 millisecond.
yeah, sorry, 1 millisecond. And, but if you go for, say, P99.9999, that might show the exact thing, but we haven't measured it.
With that, the servers can crash because the memory, because it's a memory read which you are solving.
Exactly.
So a lot of other, if a multi-core CPU, I'm from Intel, so internal guys, they always were worried about this.
Oh, I see.
And,
Okay.
because all it takes is that one instance in 24 hours, and the server could crash because now it's out of use of their channel.
Exactly. So maybe the test which we are doing now, where we are stressing the system more, maybe we might hit that. Yeah. So, and just that to continue that, we have a tiering within the device also, just to make sure that we hit the device cache as much as possible. So,
all the smart tiering, AI techniques, whatever you use,
yeah.
in the end, all it takes is that one random read which is not there, and unfortunately it's not in the nearby, because the NAND is so huge, just to look up which device to access can take such a long time, not so much effect.
It could. I'm not denying, but the RTL code which we are, it's a RTL inside the CMMH, but it's pretty efficient in getting that till now. So maybe once we stress to a level, yeah. Yeah. Okay, all right. Any more questions? Right. Thank you.